Hello everybody, this is Dr. Christopher White, and in today's presentation we're going to be looking at plate tectonics. Alright, let's get going. So the idea of plate tectonics, which is also referred to as continental drift, was put forward by Alfred Wegener in 1912. So his model helped to explain observations that were being made by geologists around that time. Now these observations, which we're going to come on to in the next slide, if you take them in isolation, are a little bit difficult to explain. However, when you put them together and put them into the context of a larger, all-encompassing geologic process, well, then all of a sudden they make perfect sense. Now, Wegener's idea was that the continents were once joined together as one large landmass, and they separated and moved to their current positions. Now, the evidence that you'll see in the next few slides backs that up wonderfully. However, there was one issue with Wegener's model, and that was it didn't actually explain the mechanism. So it showed you the evidence to show the continents were actually moving. However, it didn't actually tell you why they were moving. So that was a minor problem with his overall model. So the evidence that Wegener used was the jigsaw fit, the tectonic fit, the stratigraphic fit, the glacial fit, and fossil evidence. There's also a sixth one there, which is called the Cratonic Fit. Now that's a more recent one, and it wasn't used by Wegener, but it does also help to back up the idea of plate tectonics. So the jigsaw, also sometimes referred to as the Continental Fit. This one's the most straightforward. So I'm sure you probably realized, if you looked at an atlas when you were younger, that the east coast of South America would actually slot into the west coast of Africa quite well. Then you looked around some more, you would suddenly realize the northwest coast of Africa would actually match with the east coast of North America relatively well. Keep looking around, you might spot that the south coast of Australia would actually fit relatively well with the coast of Antarctica. So when you look at a map, you can see these points where the continents look as if they would slot into each other a bit like the pieces of a jigsaw. Now, this is actually surprisingly good evidence to suggest the continents were once joined together, because when you really think about it, what are the chances that the continents would just so happen to take on, the shapes so they would match each other, so they would lock into each other randomly? The chances are quite low. So, straight away, good piece of evidence. Now, if we were to take a pair of scissors to a map and cut out the continents and try and arrange them, we would get a fit that was good, but it's not great. Now, the problem is that the coastlines of the continents are constantly changing. They're constantly being eroded, or sediment is being deposited. And so this means the coastline is not the same coastline that was around, let's say, 252 million years ago. So, using the coastlines to match up the continents is going to get you a good fit, but not a wonderful fit. What you need some kind of margin that's more resistant to change. So, a very low rate of deposition and a very low rate of erosion. So the margin we actually want is the continental shelf break. So the continental shelf break occurs approximately 2,000 meters below sea level. And it marks the point where you transition from the continental shelf over here, which is the light blue area. So that's continental crust with seawater on top of it. And you transition into the abyssal, or down to the abyssal plain environment, which is oceanic crust with water on top of it. So this margin here, where you transition from the continental to the oceanic crust, is the shelf break, and it marks the edge of the continental crust. It's also an area that has a relatively low rate of sedimentation and relatively low rates of erosion. So the shape of the continental shelf break has not really changed for a very, very long period of time. So if you take the continental shelf breaks and use them to fit the continents together, what do you get? Well, you get this over here. So these grey lines are representing the shelf breaks, and as you can see, if you use the shelf breaks, you can actually lock the continents together brilliantly, really, really well. And so once again, the chances of the shelf breaks being able to match each other randomly, very, very low. So straight away, it's a good bit of evidence to suggest that maybe the continents were once joined together. Now, the data that supports the jigsaw fit actually improved after World War II, because during World War II there was a large amount of data collected on seafloor measurements, and obviously post World War II that became available to the scientific community, and so that helped to to refine the model a little bit. We had a better idea of exactly where the shelf breaks were, etc. So, anyway, so the jigsaw fit is the first, most straightforward and very, good piece of evidence to support the idea that the continents were once joined together. So the second piece of evidence was the stratigraphic fit. So if we look at the southern hemisphere continents only, so South America, Africa, India, Australia and Antarctica, we're not concerned about North America, Europe or Asia. So if we look at those 5 southern hemisphere continents and we look at rocks that date between 420 and 200 million years ago, we see that there are striking similarities. So you're thinking, well, okay, well, they're in the southern hemisphere, they could probably end up with the same rocks. That's not too much of a stretch. Well, it kind of is, because think about it. A sedimentary rock is a direct reflection of the environment. So the type of sedimentary rock you get essentially shows you what the environment was like. Now, we know that the continents in their current positions have very, very different environments. So let's just take 2 examples, Antarctica and Australia. In the case of Antarctica, what you have is a continent that's dry and very cold. So you have an environment that's typically dominated by glacial sediments. In contrast, Australia is an environment that tends to be quite dry and quite hot. So that's going to give you an environment that's going to have, quite a large component of desert sediments. So what you would get is you would get different types of sediments forming on those continents. So, the fact you have the same sediments being deposited across those 5 southern hemisphere continents at the same time is actually a bit difficult to do. So the question then becomes well, how could you do it? Well, there's 2 possible options. Either you homogenize the entire environment for the southern hemisphere. So you make, let's say you turn the entire southern hemisphere into, a hot, dry environment. So, all those 5 continents get covered by desert sediments at the same time. Okay? That's difficult to do. The reason is because with the continents in their current position, it affects how the air moves in the atmosphere, it affects how the water circulates in the oceans, and this has obviously a very significant effect on weather patterns. And so the ability to essentially homogenize the weather across the entire southern hemisphere is actually very difficult to do if the continents are in their current position. It's nigh on impossible, in fact. So then there's the other possibility. Well, maybe the 5 southern hemisphere continents were once joined together as one big landmass. Well, if they're one big landmass, then all of a sudden the idea of that one landmass having, one type of environment, it's not a massive stretch of the imagination, is it? Kind of makes sense. So the stratigraphic similarities that we see between these 5 continents is again a very good piece of evidence to suggest that these 5 southern hemisphere continents were once joined as one landmass. So when we actually look at the sequence of sediments, what do we see? Well, you can see we go from the Devonian, Carboniferous, Permian and Triassic. UC is Upper Carboniferous. Okay, so in this case the Lower Carboniferous and the Devonian are missing, they've been eroded away. But what do we see? Well, if we look at these Carboniferous sediments, we have essentially glacial sediments. We have glacial sediments, glacial, glacial and glacial. Excuse my dog barking in the background there. So it would seem that during the late Devonian into the early Carboniferous, it would seem that the southern hemisphere was very, very cold and you had large glaciers depositing, sediments. It would then seem that as we move into the Permian, we transition into sequences that contain coal beds. So that would suggest that the southern hemisphere environment became a lot warmer and also quite humid, because coal tends to form in quite hot, humid environments. And then as we move up into the Triassic, the sequence transitions into a sequence of sandstones, which are of desert, which are of a desert nature. So that would suggest that as we moved into the Triassic, the southern hemisphere became very, very hot and very, very dry. And remember, this is happening across all these 5 continents at the same time. So imagine what do you really think the chances are that you would be able to take the 5 southern hemisphere continents in their current position and cover them all with huge glaciers at exactly the same time? If nothing, it's almost impossible to do, because obviously you can't, the environment in Australia would be different to the environment in Antarctica, which would be different to the environment in India, etc. So, your ability to homogenize those environments, if the continents are in their current position, is quite low. It's very difficult to do. The most logical explanation is simply to take the 5 continents, push them together to make one landmass, and once you've done that, well, then all of a sudden having just one environment begins to make perfect sense. So the landmass that the 5 southern hemisphere continents form is called Gondwana, and Gondwana was one of the 2 supercontinents that went to make the most recent supercontinent, which was Pangaea. So following on from the stratigraphic evidence, we're going to look at the glacial evidence. So once again, if I just go back for 1 second, remember, if we look here, late Devonian to early Carboniferous, into the Carboniferous, we have glacial sediment. So we know during that time frame, the southern hemisphere was covered by large glaciers. Now, once again, it would be very difficult to cover all the 5 southern hemisphere continents in huge glaciers if they were in their current positions, because homogenizing those climates, very difficult to almost impossible to do. The other thing we notice is that if we look at the ice directions, so essentially the direction in which the ice was flowing, we can see that the ice was flowing from a central location, which would be around the Antarctica-Africa contact if the continents were put together as one landmass. And so these radiating ice directions from this central location is another good piece of evidence to tell us that the continents were once joined together. So here are the 5 southern hemisphere continents, and the area marked here in white, well, these are the areas where we see these Devonian Carboniferous glacial sediments. Now the red arrows are showing us the direction in which the ice was moving. And so if we put the 5 continents together and look at the directions in which the ice was moving, the ice would have been starting somewhere around here, around the contact between Antarctica and Africa, and it would have spread out from that point. Now you're probably thinking to yourself, well, okay, how do we actually know the direction in which the ice was moving? And the answer is we use these. So these are striations left by the ice as it moves over the rock. More accurately, they're striations cut by stones which are in the ice as it moves over the rock, and those stones gouge a line in the rock as they go. And so as geologists, what we can do is we can come along and we can look at these rocks and we can measure the direction in which the ice was moving. And so when we do that, and we do it across all these 5 continents, we get these directions. And it shows us that the ice was starting from this central location, and it was spreading out from that point. So, once again, very, very good evidence to suggest the continents were once joined together. So, the next piece of evidence is the tectonic fit. So, when 2 pieces of crust hit each other, it produces a mountain range, because 2 pieces of crust smashing into each other is like having 2 Hummers crash into each other head on. There's going to be a crumple zone, isn't there? And so your mountain range essentially represents the crumple zone, where these 2 pieces of crust are smashing into each other and deforming each other. Of course, the classic example of that is the Himalayas. So in the case of the Himalayas, India is smashing into Asia, and the Himalayas represent the crumple zone as these 2 pieces of crust smash into each other. So the tectonic fit, though, is actually quite helpful to us, because as geologists, we not only look at mountain ranges which currently exist, but we also look around and we find evidence for mountain ranges that existed in the past and have now been eroded away. So what we can do as geologists is we can look at the rocks, the metamorphism, and the direction and timing of deformation which produced the mountain range. And what we'll begin to see is that we'll see that some areas of the world show remarkably similar histories at the same time. So you're thinking, okay, what does he actually mean? Well, I'm actually just going to skip to the next slide. So here we go. So here's North America. We've got Canada here, United States over here. We've got the United Kingdom here, Greenland's there. We have Scandinavia here, and obviously, continental Europe's down here. So if we go to the east coast of Greenland, the west coast of Scandinavia, if you go into Scotland and into Ireland or northern England, and then you come down along the east coast of Canada and the United States, what you see is that the rocks which form this band here, well, those rocks are similar, so they're all related to mountains. They have suffered the same level of metamorphism, so as we can see they've been metamorphosed in a regional fashion, which means they were part of a mountain building event. And we can see the timing of that metamorphism deformation is the same, and we can see the direction in which that deformation occurred was the same. So if we just go over here and let's just think about Scandinavia and Greenland. So we can see the contact marked out by this red line is moving. Now I'm just going to keep it simple. I'm just going to say north-south. Okay, so the contact between the two is north-south. So that would mean the two pieces of crust were coming from the east and from the west. And so what happens is obviously when they hit each other, remember, one's moving eastwards, one's moving westwards. When they smash into each other, they create a line of mountains orientated north-south. So as geologists, we can see the evidence for the mountains on the east coast of Greenland, and we can see the evidence for the mountains along the west coast of Scandinavia. And so what we can do is we can say, right, this is when these mountains formed. This is the metamorphic history, and they have the same metamorphic history. We can see when the deformation occurred, both these rocks were deformed at the same time. And we can also see the direction. Okay, so we can see that the old mountain range on the east coast of Greenland was formed by a collision that was going east-west. And the same goes for the mountain range that formed over here along the western coast of Scandinavia. And so those pieces of evidence, when you put them together, suggest that the old mountain range that you see here on the east coast of Greenland and the remains of the mountain range you see over here on the west coast of Scandinavia is actually the same mountain range. And so that would mean that once upon a time, Scandinavia and Greenland crashed into each other, producing a mountain range. That mountain range was eroded away, and the two pieces of crust then separated and moved to their current position. And so that's the basic idea of the tectonic fit, and it doesn't just apply to mountain ranges that we see in places like North America and Europe. We see it all over the world. We see evidence for these collisions occurring, producing mountain ranges, and what we can do is we can go to very different parts of the world, and we can see that areas of these continents which are now very, very distant from one another were once upon a time joined together as part of one large mountain range. So, once again, if I was to go to, let's say, northern Norway, Scotland, maybe some northern Denmark, going to Nova Scotia in Canada and down to New England, what I would find is that the rocks in those areas showed me that during the same, at the same time, those rocks were being, were part of a mountain range, and they were being deformed in the same way. And so that tells me they were probably all part of the same mountain building event. And so that tells me those pieces of crust must have smashed into each other. So in terms of the mountain range that we see here, this is the Caledonian and Acadian orogeny, and this would be the result of Laurentia, which is North America, crashing into Baltica. Baltica is Scandinavia, a bit of northern Europe and some of western Russia. And that collision occurred 490 to 390 million years ago. So even though the mountain range it formed has been completely eroded away, as geologists we can look at the rocks and we can actually analyze them, and we can see that during this time frame there was a huge mountain range that ran along these red lines. And so we can use those mountain ranges to essentially say, right, once upon a time these pieces of continental crust were joined to each other, and since then they've moved apart. Now, the Tectonic Fit and the Cratonic Fit are almost exactly the same, in that with the Cratonic Fit we're looking at exactly the same thing. We're looking at rocks which are produced due to collisions between crust. Okay, so we're looking at the remains of mountain ranges that formed millions of years ago. Now the thing about cratons is that they are very, very old. So cratonic crust is normally anywhere between about 3.8 and 0.5 billion years old. Okay, so that's a time frame of around 3.2 billion years, 3.3 billion years. So what this means is that these cratons, they don't just show evidence for one collision, they will show evidence for multiple collisions. So they actually contain evidence that show us there hasn't just been one supercontinent forming event, there have been numerous supercontinent forming events. And it also helps us to work out which bits of crust were in contact with each other. So if we look at this diagram up here, this is a very simplified diagram of South America and Africa. And these darker brown areas represent the pieces of craton. And what we can see is that we have links between this piece of craton over here and this piece here. This piece of craton here, this piece here, and this piece here. And so as geologists, we can, link these rocks together. We can say they were deformed in the same way, at the same time, and to the same, metamorphic grade, which shows us that they, once upon a time, they smashed into each other to produce a mountain range. Now, if we look at these cratons, well, what can we see? Well, as we've just shown here, we can see that these pieces of cratonic crust for South America, were once joined to Africa. We can see that Australia was once joined to Antarctica. We can see that Madagascar, India, and maybe even some portions of Antarctica were all once joined together. And we can also see that Baltica was joined to essentially the Superior province, which covers North America, Greenland, Scotland, and Scandinavia and Eastern Europe. So we can see that by linking these cratons together, we can see, that once again, they were joined together to form one bigger landmass, and then they migrated away to their current positions. But the cratons also tell us that this wasn't just a one-off event. This is something that's happened again and again and again. So the final piece of evidence that Wegener had was the fossil evidence. Now this one is really strong evidence. So what we see is the same fossilized plants and animals occurring across some or all of the 5 Gondwanan continents. So remember, Gondwana was made from South America, Africa, India, Australia, and Antarctica. Once again, we're completely ignoring Europe, Asia, and North America. Now, when we consider the distances between the continents in their modern positions, and we know that the environments are going to be very, very different between those continents, the chances of you being able to have an animal that can live in, let's say, Australia, and have that animal be able to live perfectly happily in Antarctica, given in mind they are completely different environments, well, that's relatively low, isn't it? I mean, a kangaroo would not do particularly well standing on one of the ice shelves of Antarctica. It wouldn't last very long at all. So this is a bit of a problem. So the chances of us having the same plants and animals, across multiple different continents, given those continents have different environments, are very, very low. So this is what they found. So there are 4 species in particular which are of great interest. The first one is called Glossopterus, and Glossopterus was a tree-like plant. Okay, and examples of Glossopterus are found in South America, Africa, Madagascar, India, Antarctica, and Australia. So very, very widespread plant. We also have animals like Mesosaurus. So Mesosaurus was a marine reptile, so it lived in the oceans, but it lived in shallow water, so it was a coastal reptile. It couldn't do deep water. It wasn't built for those conditions. We also have Cynoganthus, and it was a continental therapsid. So a therapsid is kind of the intermediate stage between reptiles and mammals. And it was a carnivore. And then we have Lystrosaurus down here, and that was another therapsid, but this one was a herbivore rather than a carnivore. And so when we look at Lystrosaurus, we see we can find that in Africa, India, and Antarctica. And we can see that Cynoganthus occurs in South America and Africa. So, what would you say the chances were of a reptile being able to, essentially an intermediate reptile mammal species being able to survive in Africa and India? Well, yeah, that could possibly happen. But would you expect to find that same animal happily living in Antarctica under Antarctica's current conditions? Well, the answer is no. You wouldn't. So the question then becomes is, well, how can we have the same animal living on different continents at the same time? If we assume the continents have never moved. Okay? And the answer is that's pretty difficult to do. Okay? So once you get to that point, once you get to that conclusion, the next step is rather natural. The next step is simply to say, okay, well, if we were to take the continents and push them all together to form one big landmass, would that make the process a lot easier? And the answer is yes, it would make it extremely easy, because in that case, your animal could quite happily walk from Africa into India and then into Antarctica. And as we've already discussed, because they were part of one large landmass, it would have meant that the environment would have been homogenized. So the environment in Africa would have been the same as the environment in India, and India's environment would have been the same as the environment in Antarctica. And so all of a sudden it begins to explain how you can have these animals happily living on what are now different continents at the same time. So we just discussed what they are, but Glossopterus is a particularly interesting one. So when we look at the 5 southern continents, we can see that Glossopterus actually exists in this big dark green band here. So it's actually forming what's referred to as a climatic belt, or it's living in a climatic belt. And the best example of a climatic belt that we have now, of course, is the equator. So we know that the equator is an environment that has hot temperatures and is quite humid, so it's the perfect environment for rainforests. And so we see a similar thing occurring here for Glossopterus. We can see that in this band here, when Glossopterus was around, the environment was, it would have been something like Houston actually. Warm, little bit humid, not too cold. So what we can see here is that, number one, the environment was homogenized in this band, but number two, when you plot the locations of the fossils, you get this beautiful circular pattern, which is, as I said, which is a climatic band, and that's very difficult to achieve if you were to put the continents in their current position. Very difficult indeed. You can't do it. But if the continents are all together as one large landmass, well then all of a sudden that actually becomes quite easy to do. Now, in the case of the reptiles, so Mesosaurus, as I said, was a shallow water marine reptile. So you're thinking, aha, right, well, there's an easy one for that. It could have just swum from South America to Africa. As I mentioned, it can't do that. It's designed for shallow water. The second it would get into deep water, it would be in very big trouble very quickly. So the idea of Mesosaurus being able to swim the entire width of the South Atlantic, very, very low indeed. In the case of Cynoganthus and Lystrosaurus, well, in order to get those animals to where they are found, you would need absolutely massive migrations. I mean, let's just think of Cynoganthus here. Think how far it would have to go, assuming the continents were in their current position. So let's just say that Cynoganthus, started in Africa. Well, it would have to work its way all the way up through Africa. So it would start off. Now, I'm using modern environments as to describe what would be happening. Okay, so it's going to start off here in Central Africa in what would be a semi-rainforest environment. Then it would have to transition into the deserts of Northern Africa. Then it would have to transfer into the hotter, arid conditions of the Middle East, and then from there it would continue into the high, dry environment of Central Asia. Then from there it would have to go into the coniferous forests of Russia, and then across the Bering Strait into Alaska. Then it would have to continue down through the boreal forests of Canada. Eventually it would make it onto the Great Plains of North America. Then it would come down into Central America. It would move through the hotter, drier conditions of northern Central America, and then head down into the more hotter and humid conditions of southern Central America. And then obviously it would then have to work its way across into South America, come down the elevated conditions of the northern Andes, and then onto essentially into rainforest conditions of central South America. And then finally, as it made its way down here, it would be ending up in these semi-arid grasslands of central southern South America. So that's a pretty huge journey, during which time it has to go through numerous different environments. The problem is that an animal which is designed to exist in a rainforest setting will do extremely badly in a desert. So you can't just have Cynoganthus just stroll happily across the Sahara. It can't do it. It would die. So what would happen is your animal wouldn't be able to do that. It would have to evolve to become used to desert conditions. Then it could move across the Sahara. Then it would have to be able, then it would have to adapt to the conditions in the Middle East. Then it would have to adapt to the conditions in the elevated conditions of Central Asia. Then it would have to adapt to the forest conditions of Russia and Alaska and Canada. Then it would have to adapt to the Great Plain conditions of North America. And you can begin to see, your animal would have to go through multiple different environments, which it wouldn't be able to transition between quickly. It would have to evolve to be able to exist in those environments. So by the time Cynoganthus made it from Africa to South America, assuming the continents were in their current position, it would have had to have evolved massively. The journey would have taken millions of years. And so the animal that would arrive in South America would not be the same animal that left Africa. And so, I think that's pretty strong evidence to suggest that the chances of these animals being able to migrate between the continents, if the continents are in their current position, is very, very low. Okay. Now you're probably thinking, but hold on a minute, humans can do that kind of thing. Yes, we can, but we are extremely adaptable. Okay. We have a level of intelligence that allows us to produce tools which help us to survive in various environments, even sometimes when those environments would normally kill us. So, unfortunately, an animal like Cynoganthus would not have that capacity. So, once again, the idea of a migration is actually very, very difficult to explain to a degree where you could make a strong argument for it. So the most reasonable argument is simply to say the southern continents were all together as one large landmass, and then these animals can quite happily migrate between the continents with very little fuss. Now, when it comes to the fossil evidence, people went and said, but I can think of a way around this. We could use land bridges. Now, to be very, very clear, a land bridge is a naturally occurring feature. We have them now. Okay, so the classic example of a land bridge would be Central America. Central America forms a land bridge between North America and South America. We also have land bridges which are created by freezing. The Bering Strait creates a land bridge between Asia and North America. And we have land bridges which can be created by sea level changes. So, for instance, the English Channel. Once upon a time, the United Kingdom was attached to France, and animals could happily migrate between the two with absolutely no problem whatsoever. And then, at the end of the last ice age, the area which is now called the English Channel filled with water, and it cut off the United Kingdom from continental Europe. So land bridges are something that exist now, and we know they've existed in the past. And so people went and said, all right, well, what about the possibility of there being, huge land bridges that extended all the way from South America to Africa, and from Africa to India, and from India to Australia, and from Australia to Antarctica? And that would allow these animals to happily migrate between these continents with the minimum of fuss. Well, the answer is no. Although there are land bridges, and yes, they do allow animals to migrate, there is absolutely zero evidence for land bridges having been around that would have allowed animals to have happily migrated from, let's say, South America to Africa during the time frame that we're talking about. So there's no evidence to suggest that the land bridges actually existed. And as we've already gone and discussed, the idea that these animals could happily migrate from one of the continents to another, well, once again, that's very, very difficult to achieve. So the only logical answer is that the continents were once together as one large landmass, and that would mean the animals could quite happily migrate from one landmass to another with the minimum of fuss. Either that, or it was aliens. You never know. Okay, so this is a good place to stop because this first part has been rather long, for which I apologise. So get up, take 10 minutes, have a walk around, get a glass of water, a cup of tea, and just take a bit of time to relax and then come back for part 2.